To answer the question, let's have a close look at the payoff matrix. So, does either row or column have a dominated strategy? Does it have a strategy that it will never play? First, consider row. So, what is the best response for row if column plays left? Well, if column would play left, then the best response for row would to play middle. If instead column would play center, the best response for row would be to play middle as well. But if column would play right, the best response for row would be to play bottom, because that gives it a payoff of 2, whereas middle and top would only give it a payoff of 1 and 0. So what we get is that dependent on what row expects column to do, it will play either middle or bottom, but it will never choose top. So top is a dominated strategy for row. Similarly, for column, if column expects row to play top, then it will play left. If column expects row to play middle, it will play center. If column expects row to play bottom, it will also play center. So column will play either left or center, but it will never choose right. So for column, right is a dominated strategy. And that completes the quiz question. So if you can identify a dominant strategy for each player, then solving the game is easy, because you know what players will always choose. They will always choose to play the dominant strategy. However, in most games you cannot identify a dominant strategy, and the optimal strategy of a player does depend on what the other players choose to do. So in those cases we rely on a different concept. We rely on the concept of a Nash equilibrium, and I will explain to you next what the Nash equilibrium concept is. So the Nash equilibrium requires that an action of a player is the best thing that the player can do given the action by the opponent. So in a Nash equilibrium, every player involved in the game plays a strategy that is the best strategy that it can choose given what the other player does. And for a pair of strategies to be a Nash equilibrium, this needs to hold for all players at the same time. So let's run through an example in which we go through the dominant strategies and Nash equilibrium in a very systematic way. Suppose we have two grocery stores that each need to decide whether to build a new store, to remodel the existing store, or to leave the store as it is. And we have Food for You and Grocery Mart, and the payoff to each store are given in the matrix that you observe behind me. And the payoff matrix shows that the profits attained by Food for You, for example when it builds a new store, depend on what the opponent does. So if Grocery Mart builds a new store as well, the profits will be 200. If Grocery Mart instead remodels the existing store, then the profits of building a new store to Food for You will be 300. And if Grocery Mart leaves the store as it is, the profits to Food for You of building a new store are even 400. And we will answer 3 questions. The first is, can we identify a dominant strategy for one of the players or maybe for both players? If we can do that, we know what is optimal for the player to choose independent of what the opponent does. So it's the strategy that the player will always choose. So we know what it will always choose, and we also know that the other strategies are dominated strategies. That will simplify our life in finding equilibrium outcomes. Then second, we can ask, does either of the players have a dominated strategy? Does it have strategies that it will never play, such that we can safely ignore them? And thirdly, what are the Nash equilibria of this game? There may be one Nash equilibrium, but there may also be multiple equilibria. Okay, to start with question A. Dominant strategies are strategies that are chosen no matter what the competitor does. Independent of what a competitor does, they are optimal to play. And let's first consider food for you. So, does food for you have any dominant strategy? And suppose now, what is the optimal response by food for you if Grocery Mart decides to build a new store? Well, if Food for You expects Grocery Mart to build a new store, then it's optimal for Food for You to remodel its existing store, because then it will have profits of 400, which is more than the 200 or 150 that it would attain if it would build a new store or leave the store as it is. If instead Food for You expects Grocery Mart to remodel the existing store, then it's also best off to respond by remodeling its existing store, because then it attains a profit of 450, which is more than the 300 or 175 that it could attain otherwise. If Food for You expects Grocery Mart to leave the store as it is, then it's optimal for Food for You to build an entire new store, because in that case it would obtain a profit of 400 instead of the 300 or 350. So what we do is, for each action by the opponent, we look at what is optimal for Food for You. And we observe that in two cases it's optimal for Food for You to remodel the existing store, and in one case it's optimal to build a new store. And from this we can see that Food for You doesn't have a dominant strategy. It doesn't have a strategy that's always optimal, independent of what Grocery Mart does. And now for Grocery Mart. So if Grocery Mart expects Food for You to build a new store, it's optimal for Grocery Mart to remodel its existing store. If it expects Food for You to remodel the existing store, it's also optimal for Grocery Mart to remodel its existing store, because 450 is more than 300 or 175. If it expects Food for You to leave the store as it is, it again is optimal for Grocery Mart to remodel the existing store. So Grocery Mart finds it optimal to remodel its existing store no matter what Food for You will decide. So Grocery Mart has one dominant strategy: remodel the existing store. It's always the optimal thing to do, no matter what Food for You will decide. And that brings us to question B. So, is any of the strategies of either Grocery Mart or Food for You dominated? Well, in question A, we already found out that Grocery Mart has a dominant strategy: remodel the existing store. That is the strategy that it will always play, which implies that it will never play the other two strategies: leave the store as it is or build a new store. So the other two are dominated for Grocery Mart. And Food for You, we already observed that for Food for You, it will either build a new store or it will optimally respond by remodel the existing store, but it will never leave the store as it is. So leave the store as it is a dominated strategy for Food for You. Finally, we have to find the Nash equilibrium. And to do that, we use the check method to indicate what each firm should do in each box. And we already did that in question A, where we drew lines under each optimal payoff. And we are going to incorporate them in the payoff matrix here. And instead of the lines, we now have checks. And the Nash equilibrium is the outcome or the outcomes that contain two checks. So in this payoff matrix, we observe two checks in the element 450, 450, where both stores decide to remodel the existing store. So the Nash equilibrium of this game is unique, and it's the pair of strategies where Food for You decides to remodel the existing store and Grocery Mart decides to remodel the existing store as well. And why is remodel the Nash equilibrium? Well, given that Grocery Mart decides to remodel the existing store, the optimal response for Food for You is to remodel the store as well. And vice versa, given that Food for You remodels the existing store, the best thing that Grocery Mart can do is to remodel the existing store as well. And remember that the definition of a Nash equilibrium is that it's a pair of strategies that for each player is the strategy that's optimally to choose given what the opponent does. And remodel is the only thing, the only pair of strategies for which this holds. Importantly, if you have to derive the Nash equilibrium, then it's always an equilibrium in a pair of strategies, what people choose. So if you are asked to find a Nash equilibrium, then if you found it, you should write the Nash equilibrium of this game is remodel. You should frame it in terms of the strategies chosen. You should not say the Nash equilibrium is 450. So the Nash equilibrium is defined in the terms of strategies and not in the terms of payoffs. So to summarize how to find the Nash equilibrium, use the check method. So analyze the payoffs or the strategy combination of each player one at a time and ask yourself what is optimal to do for one player given a certain strategy by the opponent. So call our players row and column and suppose that each has two actions available. What should row do? First, ask yourself, okay, suppose that column chooses A, what is the best action that row can take? And then place a line beneath the payoff of that action for row, or a check. And the next ask if column doesn't choose A but B, what is in that case the best action for row to take? And again, place a line beneath that column. Repeat the steps for column, and if one of the boxes in the payoff matrix has two lines, that represents the Nash equilibrium. If no box with two checks appears, then the game doesn't have a Nash equilibrium. And it can also happen that more than one box has two check marks. And in that case, we have a game with multiple equilibria. So importantly, a game can have no Nash equilibrium in pure strategies. It can have one unique equilibrium, and it can have multiple equilibria. So what is a pure strategy? It's the strategy in which the player chooses a particular action with certainty, either top or center with probability 1. So the other thing is that you have mixed strategies where people choose an action with a certain probability. So if you have to kick a penalty as a soccer player, then you may mix between shooting the ball to the left corner or shooting it to the right corner. And it's not optimal for you to always choose the same corner with probability 1, because then the goalkeeper will know that and he will always dive in the right direction. So in those cases, you may apply a mixed strategy in where you mix between the two actions available to you. In this course, we're not going to discuss mixed strategies. So predicting outcomes of a game is relatively straightforward if there's one unique Nash equilibrium. Then it's unambiguous what a solution is. But what if there's more than one? If we have multiple equilibria? So let's consider the Warner Brothers Disney example from before. And now suppose that the two companies are deciding on which month to release a movie. And available actions are May or December. And March is a dominated one. So this is from the book. And Warner Brothers and Disney, they have symmetrical payoff, and it appears that there are two Nash equilibria here. So if Disney decides to release the movie in May, and Warner Brothers also decides to release in May, then they both earn a payoff of 50. If Disney opens in May and Warner Brothers in December, then all the young people can go to both movies because they don't appear in the cinema at the same time. And the payoff to Warner Brothers will be 200 and to Disney 300. Similar if Disney releases in December and Warner Brothers in May, although then Disney will have a payoff of 200 and Warner Brothers of 300. And if they both open up in December, then each will get a payoff of 0. Now this is a game with two Nash equilibria, because given that Disney opens in May, it's optimal for Warner Brothers to open in December. And given that it's optimal for, or given that Warner Brothers releases in December, it's optimal for Disney to release in May. So December for Warner Brothers, May for Disney is one Nash equilibrium. But we have a second one where Disney releases in December and Warner Brothers releases in May, because also there, given that Disney releases in December, it's optimal for Warner Brothers to release in May. And given that Warner Brothers releases in May, it's optimal for Disney to release in December. So May Warner Brothers, December for Disney is a second Nash equilibrium in this case. And that leaves us with a question: what will we observe in practice? So the two firms really face a coordination problem. So will they go for Warner Brothers May, Disney December, or Disney May, Warner Brothers December? And we don't know. So we don't know what will happen in practice, and we need to rely on information outside of the game that may predict that maybe we know that Disney has a reputation for the last 50 years. It opens in December, and we may expect that Warner Brothers takes into account that Disney has its traditional release in December, so it will choose May instead. So they, based on this information, we might say, okay, maybe they can coordinate on this Warner Brothers May, Disney December outcome. But just based on the payoff matrix, the players, the action available, we cannot decide which of the two equilibria will occur in practice and how they will coordinate on one of the two. The concept of Nash equilibrium relies on the idea, it rests on the idea that both players make rational decisions. So they choose the action that optimizes their expected payoff. And each player assumes that the opponent is a rational player. But what if you cannot make that assumption, and you cannot rule out that your opponent is a maverick, an idiot, someone who just does something, is not really interested in maximizing his or her payoff? So if other players may make systematic errors, so they don't appear to maximize their payoffs, in that situation, if you have that suspicion, then you may rely on another strategy. So you want to limit the harm that the opponent can do to you, and you may apply something that is called a maximin strategy. So you want to minimize your exposure to the potential loss. If you apply a maximin strategy, you choose the strategy that gives you the largest minimum payoff across all possible strategies of your opponent. And we will run through an example. So here's the application. We have a retired person who opens a restaurant. And he or she does so in a neighborhood that has now a single high-end restaurant run by a renowned chef. And this chef is a very rational person. But now the wealthy retiree enters and she wishes to open a restaurant in the same neighborhood. She has a passion for cooking, but cannot match the trained chef because, well, he has 20 years of experience. So the players in this game are the chef and the referee, and the strategies that they have available to them is to either decide to cater to the high end of the market or to the low end of the market. And the payoffs are as follows, and they are weekly profits, and we list the payoff of the chef at first in each box. So if both decide to cater to the high end, then the chef will clearly win because, well, the retired person cannot really cook. So in that case, the chef will get all the customers, no real competition from the other person, and the chef will earn profits of 500 and the retired person profits of minus 1000. If the chef decides to cater to the high end, whereas the retired person does the low end cooking, then the chef will earn profits of 3000. So that's even much better. No competition on the high end. And the retired person, well, cooking on the low end is easier. So she's also able to make some profits equal to 500. If the chef instead caters to the low end and the retired person to the high end, then the chef will still earn 2000 and the retired person will earn 0. And if both cater to the low end, then the chef will earn 1000 and the retired person 300. Now let's put that in the matrix. And then it looks as follows. We have the chef in purple and the retired person in green. And if both are rational, profit-oriented firms, then we have one unique Nash equilibrium, and that is that the chef will operate at the high end and the retired person will operate at the low end. Because given that the chef operates at the high end, it's optimal for the retired person to operate at the low end. Given that the chef operates at the low end, it's also optimal for the retired person to operate at the low end. So operating at the low end is a dominant strategy for the retired person. But given that the retired person operates at the low end always, it's optimal for the chef to operate at the high end because 3000 is more than 1000. So chef high, referee low is the unique Nash equilibrium. However, suppose now that the retired person has sufficient money, she just wants to enjoy cooking and doesn't care about any of the money that the customers bring in. And she simply wants to operate a high-end restaurant. So no matter what, sufficient money, I want to have this fancy high-end restaurant despite the fact that I cannot cook. So if the retired person acts in that way, well, then the chef may be better off to apply a max-min strategy because the retired person doesn't optimize payoff. So the chef cannot take that for granted. And given that she doesn't care about money at all, but she does care about high-end cooking, she will choose to operate at the high end. But then the chef is worse off by operating in the high end because, well, then he will face stiff competition and his profits will reduce to 500. Whereas if he would flip hamburgers instead, he would be able to make profits equal to 2000. So the playing low is the strategy that for the chef maximizes the minimum loss. So if he plays low, he will always make a profit of at least 1000. If he plays high end, then his profits will be either 500 or 3000. But in the worst case scenario, only 500. So his exposure to the retired person is mostly reduced if he chooses to cater to the low end of the market, because that will guarantee him a profit of at least 1,000. And if he chooses high end and the retired person doesn't care about money but just wants to do fancy cooking, then his profits will drop to 500. So the chef maxi-min strategy is to change the restaurant to a hamburger restaurant. And if the raterie does indeed decide to go high-end, the new equilibrium is given by chef low-end, retired person high-end. So, and again, I reiterate, if you are asked to give the equilibrium, do not say the equilibrium is 2000, 0. So an equilibrium is not defined in terms of payoffs, but an equilibrium is defined in terms of strategies. So you should say the equilibrium, the maxi-min strategy. If the chef plays a maxi-min strategy, then the equilibrium of this game is chef low-end, retired person high-end. And that brings us to the second quiz. So again, we have the row player and the column player, each with 3 possible actions. And what you need to do now is to determine the Nash equilibrium, or if there are more, the Nash equilibria of this game. And you should also explain why these pairs of strategies are Nash equilibriums, or one or more.